Recording. What boy? Let me see that first.
When your match.
It was awesome. I
Almost got away.
I know you did
She's so fine. You gotta walk us to every place. Cause she say so much. She's like for the youth. Yeah, before she checked in Spanish, she was like, hey.
I don't even know how she's going.
She said the late class.
Ezra, please sit down, please.
Is that a Marty?
So how do you know I was So how does this
One of these cashews for
Why do every time I get this box, I get the fancy? That's just probably this is the only class I can do. I ain't know that's what you was talking about. Class copy.
Alright, stop loitering. Go. Alright, you're gonna do
I'm talking to y'all because the sound.
Good afternoon, everyone. That's one, everybody. Take your backpacks up. Mr. Turner. Mr. Dempsey, backpack. Laurel. Mr. Smith. Backpack. Red. Emmanuel. Backpack.
Hey, Dad told me he was looking for me.
Thank you, that's two.
I didn't go.
One more time. Derek, pencil. You can play with the DS here later, please. Thank you. All right. So now that I have your attention, everybody picked up a half sheet at the door. This is your due now. We're going to be silent until 2:13. Right? We'll see.
Oh!
Don't write on that yet, but I'll let you write on that later.
This your first. They has most definitely like to slide. They not even gonna know this is going to be.
Tyson. Okay. Conversation later. Use your notes.
Oh, so it's 1 second.
That's why you gotta use your notes. Look for 10. Give me the neutral company.
Wait, hold on. How did he even get on? I don't even know.
Why you stop that just handling.
Let's do this. 1, 2, 3, and we are silent now. And because you are not silent the first 2 minutes, we are going to until 2:15. Silent do now. Do not ask me questions. Use your own notes, please. Right? I believe I just set a silent expectation. Thank you. Please have a seat, Jeremiah.
Mr. Wong.
Go back to your seat. The board's not important. It's a set.
It's based on that, right?
Hold on. Use your notes and not your voices, please. Notes you should have gotten from last week. This packet that I just gave you is a little bit new, but it also covers a lot of the same stuff that you have learned the previous week. Deborah and Destiny, please get your heads up and your backpacks on the ground. Thank you. Please put your backpacks on the ground for me. Thank you.
Never mind. Little candy logo. Stars for the we open it.
Deborah, put your backpacks on the ground. Thank you. That would be nice, Sonny. Unfortunately, they're choosing to be not play. I am done. I'm trying to find the time.
So since you shut up.
Okay. Reset. All right. Thank you. Questions afterwards? Thanks a lot. I'm going to ask you guys to stop playing, so at this point I'll give you one each. Play around. Thank you. So, what we're going to do now, we're going to silently listen and track the board. Yeah. Thank you. And I'm going to explain how to do this because I think last week we had like a little bit of misunderstanding as to how we're supposed to set up a problem like this. What I want to do is do some clarification, and that's what today's lesson is about, is clarification, because tomorrow we will go over again the same. Manuel, are you looking for something, sir? All right. We're looking for the same methodology that we've done before, but at the same time, there might be a different way that each of us can try to do the problem, and something that makes it easier for us, right? So what I would like to do is go through this one step at a time. First of all, did anybody find tin and chlorine? Okay, Laurel, what's tin?
All right.
You raise your hand. What's it? SN, right? So tin is SN. And where's chlorine? Thank you, sir. Cl. So chlorine. Cl. Okay.
Well, yo, yes.
All right. So the first question asks you about the neutral atom. Okay. The neutral atom is what happens when you have the same number of electrons and protons. So the number of electrons has to match the number of protons in order for you to have a fully neutral atom. Okay? In our case, tin, if you look at your periodic table, is in group 4A. It does have 50 electrons, but only 4 of them are the ones that we care about. Okay? Yeah. Tin. All right? So what we want is to draw 4 electrons around our tin atom. Okay? And the reason why we do it this way is because until you have 1 electron on every edge, we cannot double them up. Okay? So that's our neutral atom for tin. See that? You can write that on your. Chlorine, on the other hand, is in group 7. So what are we looking for, Jordan? 7 electrons. And the way you draw this, guys, and let's do it in purple, okay? Go 1, 2, okay, 3, 4, then 5, 6, 7. Tyson, you have a question?
I thought when you draw the dots, like they gotta be like almost touching. Like you got them.
Oh, you mean touching here?
No, I'm saying like. No, I'm saying like, do you know what the dots at? Like they not.
Oh, you're
saying
talking
they gotta
about
be like extra close. Yeah.
As long as you draw them along the edge, you can. Are you saying, like, if I were to do this, like, just do that?
Yeah, right. That's
Very
what you
close.
told me you had to do.
Yeah. So the closeness, Tyson, isn't about how close the pair of dots are. The closeness is I'm hugging the edge. So I'm going to have you guys pretend that there's a box, an invisible box surrounding this. The closeness that I was talking about is just making sure that you're lining them up along the edge. So the space in between the electrons doesn't really matter, but the space between this guy and this guy matters a lot. So you're going to do this. So this is a check mark. We want to do that. Okay? But we do not want to do that. This is where you say, no, we don't do that. So we do this. We do not do this. Okay? Okay. Martin.
You said it don't matter which way you go, like counterclockwise.
No, you can do it however you want as long as there are 7 surrounding the chlorine and 3 of them are in pairs, then you just need 1 single electron and you're good. Okay. So if your single electron happens to be down here, you're still okay. So that was a good question. All right, so now we go to part 2. Now we got to draw these as ions. So if you guys remember, if I have tin, and it has 4 valence electrons, tin is a metal. What does a metal want to do? Lose. So we're going to lose all 4 of these, okay? So we're going to lose all 4 of these. So eventually these will all go towards chlorine, so we're getting rid of this, guys. All right, when we do that, we have Sn. We just lost 4 electrons. What's my charge? If I just lost 4 electrons, I'm getting less negative.
Oh, you get it. Wait.
Which 4? Plus or minus?
Plus.
Plus 4, right? Because every time I lose an electron, I'm getting more positive.
You gain 1.
I'm going to gain an positive charge. That's right, guys. So if I lose 4 electrons, I'm going to get to a plus 4 charge. On the other hand, the electron that used to be on tin is now going to hang out with chlorine, so it'll gain an electron. And when you do that, you have Cl with 1, 2, 3, 4, 5, 6, 7, 8. If I gain an electron, what's my charge now?
Wait, you said what? If you what?
Say that again? -1, thank you, Nia. So now, we have a 10 with a plus 4 and a Cl with a -1. Okay? It has 8, but remember the charge used to be 0 with 7 valence electrons. Now I added 1 extra electron. That's a negative charge on top of 0. So that's why it's -1. Okay. Bring it back. Okay, the third question asks you to put these together into an ionic compound. I have a plus 4 charge and a -1 charge. How many -1s do I need to get rid of that plus 4 charge? What do you think?
You said I need 4.
I need 4 of these, right? So let's illustrate why that is, okay? The 10 can lose up to 4 electrons, but chlorine can only grab 1 at a time. So you're going to need 4 chlorines to grab those electrons. Another way to look at it, guys, is to say, okay, I got a plus 4 somehow.
So, yo.
Hold on. Somehow I have to get rid of this plus 4. So every time I have a Cl, I have a -1. I'm going to have that -1, that gets it to plus 3. If I get another -1, I get it to plus 2. Okay? Yes, sir.
So, you said you had to get rid of the plus 4. Wouldn't you be getting rid of it anyway? Because you gonna have to, you lose 4 anyway.
We lost 4 electrons, but those electrons had to go somewhere. So, in a way, you're trying to see, what do I do to cancel out this plus 4 charge? So we're not, I see why we're confused. We're not technically getting rid of it. We are just trying to cancel it out. Okay? So we got plus 4, -1, -1. So we got 2 more positive charges we got to get rid of. That means we need 2 more of the Cls. Okay? So we got Cl with a -1, that's 3. Cl with a -1, that's 4. So if I have a -4 and a plus 4, they will cancel each other out because plus 4 minus 4 equals 0. Okay? So that gives me 1 Sn and 4 Cls. Chemical formula-wise, what should I write? What you got, sir?
SnCl4.
Nice. So Jordan says we should write SnCl4. Again, we have 1 Sn, 4 Cls. That's why we write SnCl4. Now, here's the not so tricky part. What do we name this thing? We got tin and chlorine coming together. Bring it together. What you get?
Tin chloride.
Thank you, Nia. Tin chloride. And I bet you guys raise your hand. We're going to say tin chloride. That's great. We are done with the do now. Mr. So the second one is always non-metal, and you change it to I. Hey, pipe down, y'all.
Apologize.
For our second question, you're supposed to put that. You're supposed to put this for our second.
Yes, and make sure you have 8 electrons around the CO. So Jordan is asking a clarification question. If I do SN, remember a metal is losing all of its valence electrons, so we just got rid of all 4 of them. Now it's got an empty outer shell, it has a +4 charge, so you have nothing around the metal. But when you have the non-metal, because our rule is to get to 8, you need to show all 8 electrons around the non-metal, and then put its charge on the outside of the bracket. Nia?
Okay, so you can have more than one, you can have more than 2 fluoro.
Yeah. You need to actually have 4, because again, each chlorine can only accept this 1 electron. So you need to somewhere to stash the other 3 electrons.
So with any compound, you can have more than 2.
You can. Sometimes it's 1 to 1. In this case, it's 1 metal to 4 non-metals. But depending on how many you need to balance out the charges, you can have 1 to 1 or you can have 1 to 4. It really depends on what the charges are. Okay? All right. So, Tyson Gilmore, you are the purveyor of the cups today. All right, so you get to read first. We are now transferring to this packet, everybody, so please make sure you are on the front page. It should say page 158. Not right now.
Alright, so wait, how does it work? I suppose like...
No, you already were picked once it's...
Oh, it's just like... Boom.
Yeah.
Oh, okay.
Once... So I'm having you read first, and then once you're done reading, pick one, put it in the cup, and tell them who it is.
Alright, so what do you want me to start?
Okay, Tyson's going to read from the handle of the titanium mug. Please follow along.
The handle of the titanium... how you say that? The titanium mug in figure 1 was joined to the body of the welding. The pieces... the pieces were heated until surfaces fused together. The welding of the titanium does not take place in the air. At the temperature at which the welding occurs, titanium becomes hot enough to react with oxygen in the air and forming oxide. The oxide makes the weld more brittle and likely to break. Because titanium does not react with a noble gas such as, how you say that, argon? Argon, the welding of a titanium usually takes place in an argon atmosphere. Let me start right there. I'll keep reading.
Read the last paragraph in that section and then you're done.
Argon's name is a reminder of inactivity. It comes from the Greek word argos, which means idle and inert. Why is argon very inactive, yet oxygen is highly reactive? Chemical properties such as reactivity depend on elements' electron configuration.
Yes. Micah, did you have a question, sir? We're good? Okay, before Tyson picks the next name, just consider when I give you your snacks, you usually get an apple. If you bite into it and just leave it exposed to the air, it will get brown, right? So the idea behind this is there's oxygen in the air. We definitely need this to breathe or else we'll die, right?
Yeah.
But the oxygen in the air is also very oxidizing. That's why it's called oxygen. And when it oxidizes, it's stealing electrons from metals. In the apple itself, there is a metal known as iron. We need it for our blood so that we can carry the oxygen around. And this is why you eat apples, because they're a really good source of iron. Okay? Tyson, you got a question?
So what about when you get some fries from McDonald's and just leave it out?
They decompose because they're starches, and what's going on is that the bacteria are going to start like eating them. So that's why food starts spoiling soon after you take it out of the oven, because the bacteria in the air are actually getting on top of it and starting to digest it. Marvin!
So you said we got metal in our milk?
Yep, we got metals everywhere. So inside your bones, you've got calcium. Calcium phosphate is an ionic compound. That's why your bones are hard. Inside our blood, we have iron. Without iron, you can't carry oxygen. Inside our brains, you got a lot of potassium and sodium. Without those, you can't think. Okay? Okay, hold on. Julia. Right. It's called anemia. They basically don't have enough blood cells, and because they don't have enough blood cells, they don't have enough iron in their blood to carry the oxygen, and they can't breathe very well. Don't eat plain iron, though. Okay, bring it back. Tyson, go ahead and choose the next name, please.
Well, I have one more question.
Yes, sir.
About the apple. So, like you say, when it gets brown, it what?
It rusts. So
right,
that's.
So what about when you eat it? What does it do in your stomach?
No, you'll just digest it. You don't
But it's
necessarily
still brown.
digest the. I mean, there's going to be iron that hasn't been oxidized, and that's what you're incorporating into your blood cells so that you can carry oxygen. Okay? So there's going to be iron that hasn't rusted yet. Tyson's going to pick a new name. Go for it, sir.
Laurel Smith.
Laurel Smith. Read the next two paragraphs, sir.
Why do I gotta lie about a name?
Laurel. Yes, grown man voice. Let's go.
Yeah,
the highest occupied energy level. Bring it down so Laurel can read.
The highest, what? The highest occupied energy level of a noble gas atom is filled. When the highest occupied energy level of an atom is filled with electrons, the atom is stable and not likely to react. The noble gases have stable electron configurations and 8 valence electrons, which 2 indicates fusion.
Okay. Next paragraph, please. We'll just finish this page up, okay?
The chemical properties of an element depend on the number of valence electrons. Therefore, it is useful to have a model of atoms. Model of atoms that focuses only on valence electrons. The models in Figure 2 are electron diagrams. An electron diagram is a model of an atom in which each dot represents a valence electron. Symbol in the center represents the nucleus, the other electrons in the atom.
Okay. We're trying to get to a certain area so that you guys can get into group activity and then I can give you your snacks. So, up here I have projected for you an example that looks very similar to your figure 2 that Laurel just read about, okay? So on the next page, when you flip over, you'll see this diagram. You can use the A rule, so your group A rule, whether you're 1A through 8A, that tells you the number of valence electrons you should have around your element, okay? So if I'm in group 1A, I should have just 1 valence electron, whereas if I'm in group 6A, I should have 6 valence electrons. Where you are, dependent on the staircase here, that tells you, Jonathan, don't talk over me when I'm trying to explain something to you, so that's 1. Thank you. So the idea here is once you know which group your element is in, you know the valence electrons, and because you know whether it's a metal or non-metal based on the staircase rule, you can determine whether it's gaining or losing all those electrons, okay? Tyson, next. Okay, hold on. Before Tyson reads his name, did you have a question, sir?
Yeah, 2 metals and 2 non-metals.
They would not form ionic compounds. So in an ionic compound, you always have to have a metal and a
How do I
non-metal.
know if I'm gonna pull your name or not? I can't look.
Okay. Did you choose Jonathan's name?
Oh, he said don't choose his name like I know he's a mistake.
Come on, let's see who's next. Guys? Bring it down.
Crystal Hall.
Crystal's down here, so pick someone else.
So I can put it in this one. Aubrey Davis.
Mr. Davis, ionic bonds on page 159, read the first two paragraphs, please.
Elements that do not have complete sets of